are associated liquids, normal liquids, some are normal liquids. So liquids, we know states of matter, solids, liquids and gases. Under these states of matter, associated liquids are the liquids or the solvents in which between the molecule or within the molecule there exists a hydrogen bond. A weak electrostatic force of attraction exists. That weak electrostatic force of attraction either may be a intermolecular or intramolecular hydrogen bond. For example, your H2O is a associative liquid. It is a intermolecular liquid. Intermolecular hydrogen bond is present in water. Like in H of hydrogen fluoride, ammonia and H3. Here CH3COOH. Here C2H5OH. Like these are the associative liquid because you are in a water molecule. Between water molecule and water molecule there exists a type of bond, that is a intermolecular hydrogen bond. It is a one of the most important type of bond between two same molecules are there. That's why it is a intermolecular hydrogen bond. This liquid is called a associative liquid. Similarly, hydrogen fluoride, between hydrogen fluoride and hydrogen fluoride there exists one bond. Between ammonia and ammonia molecule there exists one bond. That bond is called a associative liquid. Associative bonds are exist. Intermolecular hydrogen bond. Now here CH3COOH associate, it forms a dimeric structure in a liquid state, like CH3 bond C double bond O bond OH. This is one molecule. And another molecule same similarly here the CH3, here the C bond OH and here the C double bond O. Between these two molecules, here oxygen of one carboxylic group and hydrogen of another carboxylic group, there exists one bond. That bond is called a hydrogen bond. It is an intermolecular hydrogen bond. These two are associate. It is the dimeric structure. Dimeric structure of acetic acid, like ethyl alcohol. Due to the presence of associative nature, your alcohols are readily soluble in water. So those are ready to associate, which are ready to form a inter or intramolecular hydrogen bond. They are ready to form a weak electrostatic force of attraction. They are readily soluble. It is a polar solvent. Even though organic compound is a non-polar, polarity is less. It is soluble in this due to the formation of intermolecular hydrogen bond. Here we know water molecular structure H2O, and here the ethyl alcohol molecular structure. This is between oxygen of water and hydrogen of ethyl alcohol. Again here water molecule, here there exists one bond. These two are not same molecule, different molecule. Ethyl alcohol and water, it is also a INTR, intermolecular, between two same or different molecules. So due to the presence of this associative nature, generally these associative molecules are liquids having more boiling points, more BP than now normal liquids. Normal liquids means here generally they are non-polar molecules. Such a normal liquids are carbon tetrachloride, carbon disulfide, benzene, like these are generally called a normal liquids. These normal liquids are also called a non-polar compounds. So are the non-polar compounds are soluble in the non-polar solvents only, that is a solubility, and these are having less boiling point than compared to the associative liquid due to the presence of weak van der Waals forces in this. There are somewhat a strong hydrogen bond is exist. Hydrogen bond strength is more than compared to the weak van der Waals forces. Based on this, so many applications are there in hydrogen bonding, and read all these applications on the basis of this associative nature in first year hydrogen chapter. Structure of water molecule, ice structure is there. Here based on this in H2O a liquid around one oxygen, here the 3 hydrogen bonds are present. Very, very important. Whereas in H2O solid, that is ice, around oxygen, here 4 hydrogen bonds are present. Very, very important. Wherever or whenever required for organic or inorganic explanation, solubility, better you remember this associative or normal liquid nature. On the basis of this hydrogen bonds only, even though oxygen, sulfur, both are the same family members, oxygen combines with hydrogen, it is exists as liquid, whereas sulfur combines with hydrogen, it forms hydrogen sulfide, it is in a gaseous state. That is due to the presence of associative nature. These are associated molecule, association takes place. It is generally a liquid in nature due to the presence of this intermolecular hydrogen bond. Water is in liquid, whereas it is a liquid. Your H2S is a gas. Here in H2S between hydrogen and sulfur, there is no such a inter or intramolecular hydrogen bond. That's why your hydrogen sulfide is a gas, whereas water is a liquid in nature. Yesterday some examples given, and based on solubility, volatility, low boiling and melting points. Read all the synopsis from material. Based on this, we'll get 1 or 2 questions in objective. Okay. Next, very, very important concept, that is MOT, molecular orbital theory. Last concept in this chemical bonding, molecular orbital theory. So before this molecular orbital theory, according to VBT valency bond theory, according to Lewis dot structures, your O2 molecule is a your diamagnetic in nature. Diamagnetic in nature. So according to VBT valency bond theory and Lewis concept, your O2 molecule is a diamagnetic in nature, because according to Lewis dot structure for oxygen molecule is formed by two oxygen atoms. Yeah, it is a Lewis dot structure for oxygen atom, and also another oxygen atom also having same 6 valence electrons. So these two are unpaired. By mutual contribution, mutual sharing, we'll get one covalent bond. One is sigma covalent and one is pi covalent. Now here it gives like oxygen between oxygen. Here two electron pairs are equally contributed and equally shared. It forms here one double bond, multiple bond, that is oxygen and oxygen double bond is present. Among these two bond, one is sigma covalent bond, another one is pi covalent bonds. The sigma and another one is pi covalent bond. According to its electronic configuration, your 1s2, 2s2, 2p4, its electronic configuration, it is the outermost orbit. Here 2 electrons and here 4 electrons are there. These two are paired. These out of 4, 1 is paired, remaining 2 are the unpaired. Same similarly, another oxygen atom also having same. These two off-filled valence electrons are involved in a chemical bonding. Off-filled valence atomic orbitals equally contributed and equally shares. It forms a covalent bond, that is a pi covalent bond, one is sigma covalent bond. Multiple bonds are present. After equal contribution, equal sharing, here this oxygen molecule, another oxygen molecule like equally contributed and equally shares like this. Between these, there exists a bond. These two are completely paired. So in this oxygen molecule, O2 molecule, according to VBT or according to Lewis dot structure, this is completely paired and also paired. Here by equal contribution, equal sharing, also paired. There is no unpaired electrons. Unpaired electrons equal to 0. That's why it is a diamagnetic in nature. Diamagnetic according to this VBTR Lewis concept. So after so many theories, VBT, whisper theory and hybridization to explain the geometry of the molecule, shape of the molecule, bond angles, bond energies and bond lengths. So many experiments conducted, so many scientists conducted so many experiments. VBT and MOT are the quantum mechanical principle based concepts. Quantum mechanics, quantum mechanical base. In a structure of atom, we'll get the quantum mechanics, quantum mechanical model of an atom. So on the basis of quantitative analysis, quantum mechanical quantitative analysis, VBT and MOT both are based on that. So according to VBT, oxygen molecule is a diamagnetic, whereas oxygen molecule is a paramagnetic in nature, proved by this MOT by Hunts and R.S. Millikan. Two people are clearly explained the concept of MOT explained by Hunts and R.S. Millikan. These two people are clearly explained, introduced to explain paramagnetic nature. Paramagnetic nature of oxygen molecule, O2 molecule. So according to VBT, your oxygen molecule is a diamagnetic, but experimentally proved by molecular orbital theory by using these two people. Oxygen molecule is not a diamagnetic; it is a paramagnetic in nature. So to explain this, and to explain the quantum mechanical concept to get the molecular orbital by using the atomic orbital, introduced one of the most important concept, that is MOT, molecular orbital theory. So according to this molecular orbital theory, your atomic orbitals linearly combines. That is the linear combination of atomic orbitals against molecular orbital. These molecular orbitals, on the basis of their energies, there are two important types are there. There are bonding molecular orbital and anti-bonding molecular orbitals. So according to MOT, molecular orbital theory, according to these two people, your oxygen molecule, to explain the nature of molecule magnetic properties, either paramagnetic or diamagnetic. Your atomic orbital, atomic orbital linearly combines. Linear combination of atomic orbitals. How it combines linearly, atomic orbitals. So after combination of atomic orbitals linearly, it forms a molecular orbitals. Such a molecular orbitals are again divided into two types. They are bonding and anti-bonding molecular orbital. By using this level diagram, energy level diagram, this is the potential energy level diagram, is to estimate some important points of MOT, molecular orbital theory. How it combines linearly these atomic orbitals. Your LCAO rule, linear combination of atomic orbital. According to this, both atomic orbitals, both atomic orbitals have same symmetry and same energy. Atomic orbitals only linearly combines. Yeah, the same symmetry means the oneness of one atom linearly combines with the oneness of another atom. Yeah, the 2s combines with 2s only. 2px linearly combines with 2px only. Or your 2py linearly combines with 2py. 2pz is linearly combines with 2pz only, and so on. This is a rule or the principle applicable only for homodiatomic molecules. So this is not applicable for heterodiatomic molecule. Only homodiatomic molecules linearly combines. Oneness of one atomic orbital linearly combines with another atomic orbital. 1s, not with 2s. So here 1s is not combines with 2s. Or here the 2px not combines with 2py. Symmetry is different. Electron orientation around the axis, around the nucleus, along or on the axis, orientation differs. These are 2py do not combines with 2pz. These are unsymmetry. They are unsymmetrical molecule, unsymmetrical orbital. By using this, atomic orbitals are not linearly combined for homodiatomic molecules. Maybe for heterodiatomic molecules, this rule or comes and it combines linearly. According to this concept, oneness of one atomic orbital linearly combines with another atomic orbital oneness. Here in this p orbital, px, py, pz, any one is considered as the internuclear axis. Remaining two are considered as the other regular axis. So here one axis is considered as an internuclear axis. That internuclear axis, first it forms a sigma covalent bond. Remaining two are forms pi covalent bonds. Here z-axis is considered as a internuclear axis. Internuclear axis, that is pz and pz forms a sigma covalent bond. Internuclear axis means your end to end overlapping takes place. The end to end overlap or axial overlapping takes place. Axial overlapping takes place. So end to end or axial overlapping, then it forms sigma covalent bond. Remaining are the px and px. It forms a pi covalent bond, or py and py forms a pi covalent bond. How it combines linearly, I will explain. How it forms a sigma and pi covalent bonds. Generally, according to this linear combination of atomic orbital, this atomic orbital, how it combines atomic orbitals, and how it forms molecular orbitals, and how many types of molecular orbitals are there. There are generally two types, bonding and anti-bonding molecular orbitals. How these bonding and anti-bonding molecular orbitals are formed diagrammatically, I will explain. Before that, story about this combination of atomic orbitals. Here, according to the linear combination of atomic orbital, these atomic orbitals almost having same symmetry and same energy linearly combines, it forms a molecular orbital. Once we can observe, these are the atomic orbital. These atomic orbitals linearly combines, it forms molecular orbital. These molecular orbitals are two types. Once we can observe this line or axis, energy, let us consider this energy is 10 kilojoules per mole, maybe. While comparing this, this is also a 10 kilojoules per mole. Now, this bonding molecular orbital energy is less than this 10 joules. And this anti-bonding molecular orbital energy is more than 10 kilojoules. Sum of the molecular orbital energy must be equal to the sum of the energies of atomic orbitals. So, compared to the bonding molecular orbitals, atomic orbitals as well as anti-bonding molecular orbitals, energy is more. Energy is more means it has generally more energy. More energy means they are less stable. Less stable means generally anti-bonding molecular orbitals between molecular orbital nucleus between electron density is very, very less. How it less electron density exists, I will explain that. So compared to the bonding molecular orbital or compared to the atomic orbital, anti-bonding molecular orbital energy is more, less stable, means there is no bond between the two atomic orbitals. And this anti-bonding molecular orbitals are generally denoted by sigma star, pi star, these are. And generally these are formed by the subtraction or destruction of atomic orbitals U. So how it subtraction or the destruction means, let us consider this is the wave function of atomic orbital A minus the wave function of atomic orbital B, two atomic orbitals, subtraction, take the square on both sides, here we'll get psi A whole square plus psi B whole square minus 2 into psi A into psi B. Now this is the A minus B whole square formula. This is bonding, anti-bonding molecular orbitals, that is a star. Anti-bonding molecular orbitals are formed by the destructive or subtraction of atomic orbitals. Once we can observe this, your psi A minus psi B whole square is equals to psi A square plus psi B square minus, from this, if we can remove something, then only we'll get these anti-bonding molecular orbitals. That's why your psi A minus psi B whole square is less than the psi A square plus psi B square. This indicates the electron density between the nuclei is less than the the electron density between the nuclei is less, and is more away from the nuclei, away from the nucleus. That's why in this anti-bonding molecular orbital between two nuclei, your nodes exist. Node means the vacant space. There is no electrons between the two nuclei. Whereas in this case, bonding molecular orbitals are generally having less energy. Less energy means they are more stable. More stable means bond is formed between two atom of an elements, denoted by sigma and pi. And generally these are formed by the additive. Additive are the subtract means additive interference. Additive interference quantitatively formed, that is psi a plus psi b whole square is equals to psi a square plus psi b square plus 2 psi a into psi b. This indicates psi a plus psi b whole square is greater than psi a square plus psi b square whole square. This indicates the electron density is greater between the nuclei than compared to the away from the nucleus. That's why your bonding molecular orbitals are formed between the two nuclei. Electron density is more. So on the is a simple diagrammatical explanation. A differences between bonding and anti-bonding molecular orbitals. There are the differences on how it forms by using linear combination of atomic orbitals. Generally, atomic orbitals are denoted by S, P, D, and so on. Whereas in this case, bonding molecular orbitals are denoted by the sigma, pi, sigma star, pi star. The sigma and pi. These are the bonding molecular orbitals. These are the anti-bonding molecular orbitals. So these atomic orbitals linearly how it combines and how it forms sigma and pi molecular and anti-bonding molecular orbitals. Linear combination by using atomic orbitals. I'll give the simple diagrammatical explanation about formation of molecular orbitals, either bonding or anti-bonding molecular orbitals. See, this is one atomic orbital A, this is the another atomic orbital B, based on their electronic configuration. Yeah, this is NS, this is also a NS. Yeah, N stands for 1, 2, 3, 4, 5, and so on. Here also 1, 2, 3, 4, 5, and so on. So S orbital means spherical in shape. This is nucleus. This also another atomic orbital, spherical in shape. Symmetry means there are positive loops. Here it is also a positive. Always take care of positive. Either bonding or anti-bonding, take care of positive only. Here positive loops means compulsory it is negative like. So here the ends, overlapping ends loop either above or below, same signs are present. That is additive. It is additive and it forms a bonding molecular orbital. According to that, between the two nuclei, electron density is more, then it forms like one important bonding molecular orbital. Now here it is plus, it is minus. Now here the nucleus. It is denoted as sigma NS. Sigma NS means here the sigma is the bonding molecular orbital. That bonding molecular orbital is formed by N energy level S subshell. Then electron density is lie between the two nuclei. That's why there is no node. Here there is no node or nodal plane. Electrons are exist between two nuclei. Bond exists. That is a bonding molecular orbital. If it is subtractive, Your opposite side loops are there, your plus and your minus. Your minus and your plus, like different loops signs are different. Now this is formed by subtractio. This is the destructive interference. Additive interference is this. Destructive interference is this. Now it forms a anti-bonding molecular orbital. This is anti-bonding molecular orbital, nucleus of one, nucleus of another one. Now here it is plus and minus, minus and plus. Yeah, there is a vacant space is there. Electrons are concentrated here, not between the nuclei. Yeah, it is denoted by sigma star ns. It is anti-bonding molecular orbital. Yeah, N stands for 1, 2, 3, 4 points 1. Yeah, there is a node exists. There is a node or a nodal plane exists. There is no electrons. That's why electron density is concentrated away from the nucleus. Away from the nucleus. That's why there is no bond between the two nuclei. So orbital overlapping by linear combination of atomic orbitals, sigma and pi bonding for S subshell. These are the atomic orbitals and they are the molecular orbital. There are two types, bonding and anti-bonding molecular orbitals. Similarly, here for p subshell, same here, this is for example one atomic orbital internuclear axis is here 2pz. Your NP, it is that NP is N start with 2 only, 2 comma 3 comma 4 like this. It is generally NPZ because they are explained Z is considered as a internuclear axis, and it is also another atomic orbital p orbital. Now this is the internuclear axis nucleus. It ends loops is plus and plus. You are combining a linear combination loops of two atomic orbitals of the same sign. It forms a bonding molecular orbitals. Either side it is minus and minus, or maybe a minus and minus, same either minus or plus, same signs loop. This is the additive. Additive takes place, that is psi A and psi B it is. Just like they explained, psi A plus psi B whole square. Then forms a sigma covalent bond, like the sigma covalent bond is formed. Like it is a sigma covalent bond, your minus and your minus, ends loops here minus and minus, your plus sign, like it is the nucleus. Your the electron density is concentrated between the nuclei. There is no space between the two nuclei. That's why it is a the NPZ, sigma NPZ. That is sigma 2pz or 3pz, 4pz, and so on. If it is subtractive or destructive interference, like it is opposite loops are present here. Now it is plus and it is minus, here minus and it is minus, sorry, it is plus, here minus. These two are combined by subtractive linear combination, then it gives like, now this is anti-bonding combination takes place. Now it is plus sign, it is minus, here minus and it is plus. Here there exists a vacant space between these two, that is anti-bonding molecular orbitals are formed. That is sigma star 2pz is formed. So the linear combination of atomic orbitals of S and P, they are the sigma ns, sigma npz. Similarly, pi atomic orbitals, bonding and anti-bonding pi bonding molecular orbitals, linearly combines in this linear combination. Some are bonding, some are anti-bonding on the basis of their energies, on the basis of their type of combination. Yeah, for example, it is a are NPOX, and another one is also it is NPX. It is after formation of a sigma covalent bond, that is the internuclear axis, remaining multiple bonds in p subshell are pi covalent bonds. Here in this combination loops ends either above or below, same loops are there. Your combination is additive combination that it forms a bonding molecular orbital. This is the internuclear axis. It forms like this. Now this is one important bond, that is plus and minus. Nucleus or electron density is concentrated between the nuclei. Now this is the bonding molecular orbital denoted pi NPX it is. Or maybe NPY also we can take based on their electronic configuration. We can take NPY also. But its loops combination may be different. Now it is subtractive linear combination takes place, plus and minus, minus and plus. Yeah, combination loops are differing. Then forms a antibonding molecular orbitals like antibonding molecular orbital means there is no electron density between the two nuclei. This is. Now it is plus and minus. Yeah, it is minus and it is plus. Yeah, there is no bond between these. That is called a antibonding molecular orbital. That is denoted by pi star 2p or NPX or pi star NPY. These are the orbitals linear combination, energy level diagram orbital combination. In objective, maybe we can expect one question. They'll create any one combination. This is belongs to what type of bonding or anti-bonding molecular orbital on the basis of MOT, molecular orbital theory. Okay, clear? Then on the basis of all these important points, finally, here atomic orbitals are one of the most important, either S or P, whatever it. These atomic orbitals are monocentric. See here, atomic orbitals are the, I'll go here. Atomic orbitals are monocentric. Monocentric means each atomic orbitals contain only one nucleus, whereas molecular orbitals are the polycentric. Polycentric means after a linear combination, the obtained molecular orbitals containing more than one nucleus, two or more depending upon the type of molecules, or depending upon the number of atoms present in that molecule or the species, it contains more than one nucleus. That's why atomic orbitals are the monocentric, molecular orbitals are the polycentric. Now here in atomic orbitals, electron filling takes place according to Pauli's exclusive principle, Abba's principle, as well as Hund's rule or Hund's rule. Same principle takes place in molecular orbitals also. Filling of electrons in respective atomic orbitals or in molecular orbitals takes place wherever or whenever required on the basis of Pauli's, on the basis of Abbas, on the basis of Hund's rule takes place, how it influences. While explaining energy level diagram, I'll explain all these three important rules. Okay? Energy level diagram for molecular orbitals by using linear combination of atomic orbitals of homodiatomic molecule or heterodiatomic molecules. energy level diagram for homodiatomic molecules or heterodiatomic molecules or any other molecule or the species on the basis of MOT, molecular orbital theory. Now here, first I'll give the electronic configuration of species with 14 electrons with below or up to 14 electrons, means your atomic number 7, that is nitrogen atomic orbitals. That is increasing order of their energy level electronic configuration, that is sigma 1s, sigma star 1s, are the sigma 2s, sigma star 2s. Now it is pi 2px equal to pi 2py bracket, because both are having same energy. Then here the sigma 2pz, then again start here bracket pi star 2px equal to pi star 2py. Then next one is sigma star 2pz, it is sigma star 2pz. So instead of this 1s and sigma star 1s, we can take kk energy level. This is continuous. Then here electronic configuration of species or molecule with above 14 electrons species, that is kk, first energy level like same, sigma 2s, sigma star 2s. Here the difference is this 2pz orbital we can write here in this case, that is sigma 2pz pi 2px equal to pi 2py, then pi star 2px equal to pi star 2py, then sigma star 2pz. So are they up to 7 atomic number, above 7 atomic number? Atomic orbitals. 7 plus 7, 14. Above 7 means, above 14 means 8 onwards, oxygen onwards. So here and there electronic configuration difference is here only difference. What is the main difference between below and above 7? Sigma 2pz. Why the people are written here only scientists? I'll explain, will explain the energy level diagram. So a simple rough diagram, increasing order of their energy level, 2 atomic orbital. This is one atomic orbital, this is another atomic orbital. Linearly combined. This is the ONS, this is the ONS. Linearly combines, it gives bonding and anti-bonding molecular orbital. This is the AO atomic orbital, this is the AO atomic orbital. Already in theory explained, these 2 atomic orbital energy is more than compared to the bonding. But these 2 atomic orbital energies are less than the anti-bonding. That's why this is a bonding molecular orbital. This is the anti-bonding molecular orbital. This is denoted by sigma. This is denoted by sigma star. 1s. This is 1s. Similarly, it is 2s. Your next higher increasing order of their energy level is 2s. This is the 2s and 2s atomic orbital. Sigma 2s. They are the sigma star anti-bonding 2s. After 2s, it is 2p. Here also 2p. They are considered as Z is considered as internuclear axis. That's why now we'll take first one is internuclear axis Z. Sigma is with this 2p Z. According to VB theory, of formation of sigma bond, only pi covalent bonds are formed. While writing the electronic configuration, first we'll write pi, then we can write the sigma, but while forming, first it forms a sigma covalent bond according to VBT. But in this arrangement, this is the below 7, atomic number up to 7, that is 14 electron molecular species. For this lower energies pi 2px and pi 2py. That's why your lower energy is this. The next one is 2pz, but here above or below whatever it higher antibonding molecular orbitals are having same. This is the pi 2px and this is the pi 2py. This is a sigma 2pz. This is the pi star 2px, pi star 2py. This is the sigma star 2pz. Here, electronic configuration increasing order of their energy levels 1s. Then increasing order sigma star 1s, 2s, sigma star 2s. Then pi 2px, both are having equal energies. Pi 2px and pi 2py. That's why in bracket both are equal. The next higher energy level is sigma 2pz. The next one is pi star 2px, pi star 2py. This is a sigma star 2pz. While writing this energy level, why are the 2pz is higher than compared to the pi 2px and pi 2py means, according to the nuclear model of an atom, below 7 or up to 7 atomic number, nuclear force of attraction is more and more influences on its outermost orbits. The sigma 2pz, if you can write here, this is a sigma star 2s and sigma 2pz, both are intermix. So are they to avoid the intermixing of sigma star 2s and sigma 2pz molecular orbitals. Just rearrange their energy level, that's all. This is a very, very important concept. Same, similarly, same energy level, above 7 atomic number, just one sigma 2pz. According to experimental analysis, above 7, its intermixing nuclear force of attraction slowly reduces, then immediately arranged like lower energy sigma 2pz, higher energy levels these. I'll write here, just observe here. So I have the above 7 energy level diagram like this. This is the 1s energy level diagram as it is we know as below 7. Then it is 2s energy level diagram. This is 2s. Now it is 2p energy level diagram. Now here we can take sigma 2pz. Now this is a sigma star 2s. So above 7, these two are not intermix. Do not intermix. After atomic number 7, its nuclear force of attraction. Distance increase, nuclear force of attraction decreases. Then here we can write here like. Then here same. Both the cases here above antibonding molecular orbitals are same. This is the sigma star 2pz. This is the pi star 2px, pi star 2py. This is the pi 2px, pi 2py. It is sigma. Now here the sigma 2s, sigma star 1s, sigma 2s, sigma 1s. Same energy level. Instead of this sigma 1s and sigma star 1s in both the cases, we can write a kk energy level. By using all this, in examination NEET or any object examination, while taking a correct answer, somewhat difficult to remember all these energy level diagrams. Compulsory based on this, they'll ask some important points, how to calculate the bond order, bond length, number of sigma bonds or the pi bonds, how many pi bonds and how many sigma bonds are present, how many bonding and how many anti-bonding molecular orbitals are present. Clearly they'll ask, while filling the electrons in this according to above principle, lower energy level. We know above principle, filling of electrons takes place according to the increasing order of their energy level. So here regularly takes place up to here above principle. While filling here electrons, Hence rule takes place, because these two are having same energy levels. According to Hund's rule, same energy atomic orbitals are filled with the equal number of electrons with the single electrons. Then remaining electrons are paired up if it contains. That's why Hund's rule involved here. And each and every one atomic orbital can accommodate a maximum 2 electron with opposite spin. One is clockwise and one is anti-clockwise. That is Pauli's exclusive principle. So I'll filling the electrons in molecular orbitals. Here, above principle, Pauli's and Hund's rule takes place. All the three principles are involved here. So on the basis of your MOT, all the molecular or bonding or anti-bonding molecular orbitals all are filled with electrons or vacant orbitals are present. Now here magnetic behavior, n is equals to 0 means number of unpaired electrons 0. 0 electrons are there vacant, or maybe a paired, completely paired electrons are there. In such cases, they are generally diamagnetic in nature. Very, very important. Vacant means all these are the vacants, or maybe it contains here 2, here 2, here 2, here 2, here 2. There is no single electron, there is no unpaired electrons. That is diamagnetic. And its magnetic moment m is equals to mu is equals to square root of n into n plus 2 bm. This answer also equal to 0. Now your magnetic behavior MB in this case n is equals to 1, 2, 3 unpaired electrons are there. Number of unpaired electrons are present. On the basis it is a paramagnetic in nature. Paramagnetic in nature. Now its magnetic moment of mu is equals to something is there, that is calculated by using n into n plus 2 bm. Bohr magneton. Very, very important magnetic behavior. To explain that magnetic behavior of oxygen molecule, that is above 7, that is oxygen molecule contains 16 electrons, base of 16 electrons. With the help of rough diagram, tomorrow I'll explain how to fill the electrons in these energy levels above and below 7 atomic number elements. Now here one more important point is on the basis how to calculate its bond order. So already bond order is calculated on the basis of resonating structures, but whereas on the basis of MOT, molecular orbital theory, its bond order is generally on the basis of MOT, molecular orbital theory. Bond order BO is calculated by using 1 by 2 into NB minus NA formula. Here NB is equals to total number of electrons present in B stands for bonding molecular orbitals. Your NA, your A stands for total number of electrons present in A stands for antibonding molecular orbitals. Bonding molecular orbitals and antibonding molecular orbitals means don't count the atomic orbitals while calculating the magnetic behavior or bond order or related points based on MOT. Better you concentrate central molecular orbitals, either a bonding or anti-bonding. Sigma 1 is, sigma star 1 is, sigma 2s, sigma star 2s. Like concentrate on this only. Yeah, number of electrons maybe 2 are there. Yeah, number of electrons 2. Bonding electrons 2, anti-bonding molecular orbitals are also 2. Both are the same. Here again 2 are there. Total here bonding here 2 and here 2, 4 are there. For this, here bonding molecular orbitals are 4. Antibonding molecular orbitals are 2. These are antibonding. Like by using energy level diagram, we can calculate the number of bonding and antibonding. By using this, we can calculate bond order BY is equals to 1 by 2 into NB minus NA. That is 1 by 2 into 4 minus 2, that is 2 by 2, that is 1. That one bond indicates one single bond is present. Single bond is present. That's why your bond order BO is equals to 1 bond, 2 bond, 3. It is a single bond, it is a double bond, it is a triple bond is present on the basis of this bond order. So based on this bond order, tomorrow I'll discuss some important applications about bond order, and I'll give a very, very important trick, last an important point based on bond order, without any diagrams, how to calculate its bond order. On the basis of bond order is to estimate its bond length or stability, which is more stable, less stable, or unstable. You can expect to guarantee one question. Tomorrow I'll complete neat assignments and I'll start a new lesson if it is possible. Okay, thank you, take care.